All right, I'm ready for B. It's asking the rate of change of the area. And this latter, remember that the area is 1/2 the base times the height. So if I look at my triangle, my base is x, my height is y. So my area is going to be 1/2 x times y. So that you're always looking for the relationship. In this case, the relationship between area and those two sides. And we're going to find the derivative of this with respect to t. So this side, if I take it with respect to t, I get dA dt, but this side is going to involve, you guessed it, product rule. So I'm going to just let this be my first and then times the derivative of the second plus the second times the derivative of the first. And when I do that, I get, so 1/2 x, that's your first. And then the derivative of y is dy dt plus second y times the derivative of 1/2 x is just 1/2, and that x goes to a 1, and then you have this dx dt. And I'm going to come up here and take a look at this. I've sort of rearranged it so it looks a little better. So I've got 1/2 x dx dy dt plus 1/2 y dx dt. So that's a little visually pleasant. And now what I want to do is find dA dt. That's the question. And I should have x dy dt, y, and dx dt. Do I have those things? I do. Remember, x was 5, that was given, and then we found y using Pythagorean theorem on the last video. We also found dy dt from part A was -5/12. This is 1/2, y was 12, and dx dt is 1. And if you simplify that, you get about 118/24, which is 4.958, which means the area is increasing by 4.9 square feet per second. Now notice the unit. A is in square feet, that's area, and T is in seconds. So this is square feet per second. And so I can conclude that the area is increasing by 4.958 square feet per second. And while I'm at it, I'm going to go ahead and do C. C is a little trickier because we are looking at the angle theta. We have an x is changing, y is changing. This is constant. So I need a relationship between this angle and the y, the x, or the 13. We have a choice. We can use tangent, we can use sine, we can use cosine. If we use tangent of theta, we get opposite over adjacent, and then I have two variables. I thought I would try it with one variable. So I was going to use cosine. So the cosine of theta, oops, I didn't write it down. So the cosine of theta is adjacent over hypotenuse, right? Adjacent over, you could use sine, you could use tangent. But this way, when I take the derivative, I only have to take the derivative of cosine and then 1/13 x. So the derivative of sine theta is negative sine theta d theta dt. And then I just pulled out that 1/13 and took the derivative of x, which is 1, and then you have this dx dt. And now I need to substitute in for sine theta, and I also need to substitute in for dx dt. Now dx dt was given, it was 1, it was given in the beginning, but what about sine theta? And I am going to take a look at the triangle over here. At the time when this is 5 feet away from the wall, we have a 5, 12, 13 triangle. So my sine theta is going to be opposite over hypotenuse. So it's going to be 12/13, and that's what I put in here, 12/13, with the negative out here, times dx dt is equal to 1/13 times, that was just a 1. And now I'm going to multiply both sides by -13/12 to solve, and that gives you -1/12. So I can say the angle is decreasing by 1/12 radians per second. Notice that that's a unitless measure, 1/12, which is what we get here, a unitless measure, when we do all the division. If we wanted to convert to degrees, we would have to multiply by 180 degrees over radians and get the 4.77 degrees, but this is fine. The angle is decreasing by 1/12 radians per second, or if you wanted to convert to degrees, you may. And that takes care of problem number 3. I'll be back for problem 4.